please. My presentation, if we're recording. Online class, you just joined us. We have a recalcitrant Windows machine that has decided to update itself, so we've been kind of watching things load here for a little bit. Pardon me while it catches up here. We've managed to open 10% of the morning presentation in PowerPoint. Anyway, for those of you who turned in a project submission early, or not early, but by the first deadline, I will make notes on those and get them back to you. It will be, I will try to do it before I leave from work today. If I don't, it will be, I'm out of town all weekend, so it'll be Monday before I get them out. If it ends up being Monday, because I can't push back having to leave for out of town because of commitments, if it ends up being Monday, I will extend the deadline. If I get it done today, we'll hold that deadline. Again, if you got it in by this morning, I'll grade the first one. That is your grade if you like it. If you want to take that, respond, and update it to reflect my comments and improve it, then I will grade it a second time, and you'll keep the higher of the two grades. Okay, thank you. Let's try this again. Once more with feeling. Downloads. OSI 1 and 2, high rate pans. That's us. Well, we got further. There we go. You ever get a feeling some days you just really shouldn't have gotten out of bed? This is one of those days. I'm a little concerned about driving up the highway this afternoon. Third time's a charm, maybe? Yes. For all the work we do in this field, there are days when a notepad and a pencil look really, really good. U.S. mail and the stamp. That's all I need to move data. Okay. So what we're going to do is continue our discussion about PANs. Admittedly, this is mostly for us just kind of looking at what's available, defining some terms, looking at how things have been solved. I will get a quiz up on this. There's no sense in doing an exercise because there's nothing to practice. So what I'm going to do is basically put up a quiz. You will need to, you're of course welcome to use notes on the quizzes. Basically what I'll be testing you on is the presentations here and the material in the book. I cannot believe I'm sitting here watching this happen and it's just not going to talk. You ever have that dream when you stand up in front of class and you've forgotten your pants or something like that? That's what this feels like. You know? Yeah, I guess I can. Well, there we go. Except I do a ton of this with animation. Okay. Pardon me, everybody. Shazam. Taking me back to my childhood. There we go. Okay. From current slide. Thank you so very much. Okay. So what we're looking at in this presentation are high rate PANs. Basically what went on in this is we defined low rate PANs, and we've talked about those, how they work. We've related them to the OSI layers 1 and 2 and kind of looked at how they do. Remember that the original reason for doing this was to replace cable connections to peripherals, you know, low-speed data like RS-232 ports, keyboards, mice, that sort of thing. Great idea. It was wonderful. Caught on in a huge way. And it was so nice to be able to get rid of a lot of the cabling behind things that started looking at it for other things, like video, like high-speed control channels, like audio, things that take more data bandwidth than Zigbee or Bluetooth provide. Now, they can handle audio. We looked in Bluetooth, of course, and it can handle telephone-grade audio, 64 kilobits a channel. That basically means 4 kilohertz audio, which you don't really realize it when you're on the phone because your brain is really good at filling in missing information. But an awful lot of the audio information has been removed from a phone signal. When you compare it to a full band signal, it sounds kind of like you're talking through this. We make up for it so we don't worry about it. But when you're talking about entertainment systems, if I spend money to get, you know, my Blu-ray HD Dolby movie, I'd kind of like to be able to hear all the, you know, orchestra and the cannons booming and all that. So the high quality audio, and that takes more bandwidth. You can real quickly get above the bandwidths that are in these channels. Now, when you start talking about video, forget it. Remember Mr. Nyquist? He's the one that looked at Shannon's theorem and came up with the limit for coding. Well, if you'll recall, the Nyquist limit is a lower limit of the number of samples you have to take to correctly represent a signal. Nyquist says you have to sample the analog signal at a minimum of twice its highest analog frequency. Okay, in audio, the limited audio I was just talking about, that's 4 kilohertz. So I'm going to have to sample that at 8,000 times a second. Those particular samples, we use 8-bit samples to set the amplitude. So 8,000 samples per second, 2 times 4,000, times 8 bits means 64 kilobits. That's a voice grade signal. Video's highest frequency is about 5 megahertz. So we're going to sample it 10 million times a second, and we've got to define color and brightness for every single one of those samples. You get a lot of data really, really, really fast. You can't do video over something with this kind of bandwidth without compressing it very, very, very heavily. It's possible to do, but it looks really bad. You've seen it. It's that sort of, you know, Max Headroom. Anybody remember Max Headroom in reruns? Oh, you guys missed out. Never mind, I'm showing my age. So what we ended up doing was taking the idea of a PAN, very short range network, basically to replace cable, but making it run faster so that we can replace cables that carry signals that are much more information dense, if you will. Looking at some of the rates, and these are just some that are, this is sort of a generalized table, this out of your textbook. If you look at the a high definition audio and video signal requires 3 gigabits. That's a fast link. That's a fast link on cable, much less across a wireless interface. Okay. Remember our little rule of thumb for how all things being equal, how does a wider bandwidth channel compare to a narrower bandwidth channel in terms of distance? The wider the signal, the shorter distance we can go. Well, we've just gone from at the highest, a little less than 750 kilobits to 3 gigabits. And if you go on down this list, you see some pretty, I mean, none of these get below tens of megabits. So we've got a pretty big problem here. It's going to be a low power service because we're trying to keep personal area network. We've defined that as 5, 10, maybe 30 feet. So we got to play with this a little bit. I'm going to define a couple of terms here that you will see, and in fact they're in this chart. You see source and sink. In these systems, we're acknowledging the fact that an awful lot of the time we may only be sending data one direction. Typically with peripherals, like we support in Zigbee and Bluetooth, that's not true. We're typically going to send information both ways. If I have a wireless keyboard, I'm going to send information to the device. Okay, that's a one-way. If I'm doing wireless data transfer between devices, I'm going to do that both directions. Okay, so we have both chances there. If I'm doing high-definition video and audio playback, I'm going to send that to a television. There's no real reason for it to send back data. So we're kind of acknowledging that's going on, and we're actually putting in the specification a way to talk about that. And the terms are source. This is going to be our device that is going to transmit data across a PAN, and sink, which is the device that's going to receive that data. Those are actually electrical engineering terms. You source current or sink current. You've probably run into it in your EMT studies. In this case, what we're saying is sourcing data is the transmit end of this, syncing data is the receive end, and we're not going to worry about sending anything the other way. So you kind of have to read into the specs to get an idea of exactly which link is doing what. We're not even going to go into it that far. I just want you to be aware of these terms and how they're used in the spec. Excuse me. So what we end up with is a system that looks like what we've defined a PAN. We have a device over here. We have a peripheral over here. We're going to connect them with a link, and I'm going to send data across that instead of connecting them with cables. The big difference, I'm going to move data a whole lot faster than we've been doing it before, which makes our job harder. Okay. I might even be able to support multiple streams across this. For example, if I have one cable box and I want to watch one show and my kids want to watch another one, maybe I need to be able to deliver 2 streams from that box. Okay, now I've just made my job even harder yet. Remember, these are consumer products, and they're trying to meet the demands of consumers. I know they try to shape our wants and all that, and that's fair. But they also know they also know that most people are going to watch 2 different channels. We may even include, since we're doing high-speed data over a fairly short range, we might even want to support very high-speed local area network data. If you're a gamer, you can appreciate the advantage of doing that. I'm not one. I've decided to stay Stone Age in that particular part of the world. But I've watched gamers, and think about what you're moving. There's a lot of processing power on one of these, but processing power has to have something to feed it, and you feed it lots of data. So for those big, really pretty, heavy graphic games, I need to deliver an awful lot of information to this device. Okay, so we're doing a PAN. We're just doing it with a lot more data, and we've got some restrictions on it. Okay. Now, we actually took 2 or 3 whacks at this. First one was 802.15. Again, that is the PAN part of things. And if you'll recall, we looked at 802.15.1 and 802.15.4. 802.15.3 were high-rate PANs. And the first time we did it, I'm saying we like I had anything to do with it. The IEEE actually took a whack at this. And they essentially took the Bluetooth idea and just simply sped it up. And they sped it up to the whopping speed of 11 megabits to 55 megabits. We've already discussed the rates we're talking about, and that's way below what we need for video and audio, particularly HD video and audio. So it's just too slow. In addition, they did this at 5 gigahertz, where 802.11a and 802.11n, although it hadn't when this was going on, 802.11n hadn't been specified, hadn't been rolled out yet, but they were talking about it. And there was concern about interference from existing services with the way they implemented that. What came out of this is an awful lot of research into how we could accomplish this very high-speed data channel using radio frequency in a fairly limited environment. And as you can imagine, there's more than one way to do this. The major reason you never saw this rolled out is there were two industry organizations that were working on this, and they came at it from different directions. They made different assumptions about what this product really should do, and so they approached the specification differently. And they just really could never decide on what went on. They came back in, retried this with something called 802.15.3a. We're going to try again. And the industry organizations are still going at it. They were still trying to fight it out. One of them basically had come up with something called direct sequence. Remember, spread spectrum techniques, one of the ones we looked at was something called direct sequence. It's where we put a spreading code on, and basically we use different spreading codes to separate users in that bandwidth over something called UWB, ultra wideband. We'll talk about that in the last slide of this presentation. Another group was using something called multiband orthogonal frequency division multiplexing. This is frequency division multiplexing on steroids. Basically, instead of taking one carrier and putting a stream down it and taking another carrier for another user and putting a stream down it and taking another carrier for another user and putting a stream down it. Sorry, thank you. All the noise in the online class was because my mic dropped off, and one of your compatriots in this room told me about it. In multiband OFDM, basically what we're doing is taking multiple carriers simultaneously, coding part of the data we need to send on each carrier, and then sending them across a link. It's in common use. 3G and 4G cellular both use that technique in various ways. It is a well-understood technique. There were some arguments about whether it was appropriate or the best way to do this. UWB is actually a relatively old technology, comes from the 60s, but it was used primarily for radar. And this is one of the early times it's been used elsewhere. And again, we'll talk about UWB in a second. The upshot of this was at the end of A, we had these two competing ways of doing things. We couldn't agree. Industry couldn't agree, so that was sort of the end of it. A little later, 802.15.3b came out. It basically took this and did some reverse cleanup. You know, it made it more compatible with the earlier PAN standards and things like that. It was not a major change in what was going on. Then we got to 802.15.3c. Okay, third time up to bat, or actually fourth time up to bat, let's see what we can do. What they came up with, got a little further along, decided to go way higher in frequency. These other systems, I said 802.15.3 used 5 gigahertz. They had looked at several frequency bands when they got into the A version of things. By the time we got to C, use of the 60 gigahertz band was looking pretty promising. For one thing, they'd figured out that they could do this with electronics affordably and predictably. That's one of the key things for a consumer product. Second, by moving to 60 gigahertz, I have lots of bandwidth that I can use. And since path loss, what are the variables in path loss? Distance and frequency, okay? We know what the distance is for this system within pretty tight confines. We know this is going to be something that's essentially in the same room. That doesn't make problems go away, but it puts them within a fairly tight set of constraints, so I know what's going to happen to path loss using this frequency. By going that high, I can use lots of bandwidth because there's nothing else around up there. There are some radar systems, admittedly, and this is actually in a little slice in between some. But there's really nothing else around, so I don't have to worry about existing systems or anything like that. The result out of this generically is called millimeter wave personal area network, and it can operate at better than 3 gigabits. That's the standard out of 3C. Millimeter wave is sort of like, it's the wavelength way of talking about these frequencies. If I say, you know, from our earlier discussion, if I say 10 meters, I'm talking about a wavelength of 10 meters long. This just simply means the wavelengths are measured in millimeters. Very, very, very short. So that move means we now have a wideband capable system. You know, we have a standard for it that can operate within the confines of a room and isn't going to interfere with anything that's already out there. We still have our disagreement in the industry, but we've made a lot of progress in solving this problem of moving data, very wideband data, short ranges, quickly. Okay, I mentioned there were several groups going on, and what's happening is our market process going on. It's messy. A lot of the world looks at it and says, why do you allow that? Sometimes I agree with them, sometimes I don't. But what's going on is you have 3 real systems, 3 technologies that came out of all of this. One of them adheres to the 802.15.3c standard. The other 2 came out of the research but don't adhere to the standard. They're all in the marketplace now. You can buy them right now. This is going to be a VHS Betamax videotape thing. That's way before your time, but Sony championed in the early days of home video recording. Sony championed a system called Betamax. Panasonic championed a system called VHS. You've seen VHS. Those are those things that nobody plays anymore. They sit on the shelf, and they've got a player that looks like you can stuff a sandwich in it. Why do I say that? An unnamed child of a friend thought that's precisely what that was for. Beta was technically superior. It lost. That's why everybody uses VHS. We've got the same thing going on right now with wide, high-rate personal area networks. The market's going to settle probably on 1, possibly on 2 competing systems. There's a reason one of these systems actually focuses kind of on a different area. The other 2 look at that multimedia way of doing things. How am I doing on time? I've gotten way off because with all the problems we had early. Okay, got 10 minutes. So WirelessHD is one of the systems. This is actually the one that came out of a group, an industry group, and it uses a 7 gigahertz wide channel at 60 gigahertz. So you have your box. We generate a 60 gigahertz signal, and I can support rates. It rolled out supporting rates at 4 gigabits. It's capable of data rates of 25 gigabits. That's hard to do with anything short of fiber in the cable world. You know, so this is truly impressive to be able to make this happen. I'm sorry? You know, I don't have cost information, but I know it's consumer level. You know, so I mean, it's, my guess is you're probably looking in the high hundreds, low thousands, or something like that. WirelessHD is the only one of the technologies in the market that actually adheres to 802.15.3c. This is what we defined out of the market. It's primarily pointed at doing audio and video, both standard resolution and HD, between a media source, you know, Blu-ray player, streaming from cable systems that we don't have yet to support that. That kind of high quality audio and video system, and sending it to display devices. It also supports high rate data, so you can do things like gaming across a data channel. WHDI is a second technology that's out there, and this is actually pushed out by something. Actually, I've got my notes wrong. This was pushed out by an industry group, and it is pointed at audio and video. It does a little more. I'm seeing their product line. I was kind of looking at what products were available for each of these, and I'm seeing it kind of segment the market a little bit. This standard, or this technology, I should say, it's not a standard. This technology operates at 2.4, 5, and 60 gigahertz. So basically, we are operating in the same frequency space as 802.11 at 2.4 and 5 gig. So we have some interference potential. They swear up and down. Oh, no, it won't interfere. Well, of course they do. They're trying to sell you a product, and they're using these two bands because they're trying to leverage the fact that there's an installed base out there and lots of chipsets and stuff like that that already work at these frequencies. So that's the mindset behind it. 60 gig is a new thing. We've done it. We can do it. It's harder. It's not an established way of doing things at the consumer grade. Notice the data rate, 7 gigabits. Above where the wireless HD started, but way below what it's capable of. You think about this essentially as a wireless HDMI. I'm going to take my HDMI cable that carries audio, HD video, HD audio, Ethernet, control signals, and all that, and rolls it into one interface, and I plug it across. Those are those $20 cables you have to buy nowadays. Essentially what I've done is move HD or HDMI across a wireless interface. That's a good way to think about this. And it's mostly pointed at consumer for displaying television stuff. They're also trying to get in the market of doing this kind of thing without cables. So I'd walk in with my pad that has a WHDI interface. I would connect to this projector that's a few feet away, and I can do all of this wirelessly. Pretty good niche market. I've also seen products in this for broadcast. One of the big problems in a broadcast facility is how do you get those high-quality signals from the studio floor into the back room. It's done with a lot of copper right now. And it'd be pretty nice, particularly for remote systems, to be able to roll out a sports game, set up 3 or 4 cameras, and not have to run cable to it. There's a day of setup and running all the cable for that sort of thing. So there's some products in that. WiGig is Wireless Gigabit Alliance. This actually is a subgroup of the Wi-Fi Alliance. So as you can imagine, this looks and feels a lot more like Wi-Fi. And in fact, when you go in and take a look, it's more pointed at the computer. I'm going to dock my computer and then use other wideband peripherals. I'm going to dock my computer here and use my big display over here. Oh, by the way, I'll have a keyboard, great audio, wideband, Ethernet, all that sort of thing. It looks real similar to the one we just looked at. 2.4, 5 gig, 60 gigahertz as a new band, supports 7 gigabit links. Think about this as a really fast wireless USB port. That's kind of the market niche that they're going for. And most of the applications you see are going to show things that are more along the line of using your computer across a wireless link than using media stuff. Obviously, if you can do things at this rate, I can move media across that. You've watched movies on your computer, so I can do that. But they're kind of pushing other applications other than just moving movies and such as that. Write this down if you like, and you can either call me a fool in 5 years or say, boy, you had a crystal ball. My guess is you're going to see the wireless HD and WiGig survive. I don't think you'll see, and I'm just drawing a blank, I don't think you're going to see WHDI survive. Maybe you will. Maybe the market will support it enough. We have way more users of this kind of technology potentially than we did of, like the home video analogy I use. There's much, much larger potential market, so I can afford to cut that market into smaller pieces. Maybe they'll all survive. Okay. Part of the problem with this, all of these use the 60 gigahertz band. Two of them don't have to, but there's a lot of advantage to using the 60 gigahertz band in there. You've got a lot more bandwidth available. And if you dig into those specs, their highest rates are only available at the 60 gigahertz band. So when we do that, we've opened, they're not different problems, but moving that much up in frequency. We moved up a decade in frequency over what we've been talking about. Heretofore, we've basically been talking about 5.8, and you saw what kind of path loss you got in your problem. Now we're 10 times that high. So our loss has gone way up. Because we're talking about a personal area network, we can actually control that somewhat. And we can make pretty good assumptions about where people are going to use this kind of thing. So the distance part's actually controllable, but when you get that high, radio tends to act an awful lot like light. These frequencies require a line of sight path. Okay. Now the Fresnel zone on these things is only about that big. Remember, Fresnel zone's based on frequency as well and on distance. Okay. So Fresnel zone's not really a big issue here, but I do have to have a direct line of sight. So if I have my media device on a shelf, and my television's over there, and there's a chair in between, now we've got an issue. So what some of these systems use is something called beamforming, which we actually met in one of the earlier chapters, and basically we just talked about it. Beamforming uses the same physics as multipath cancellation. We talked about this as a problem. Remember, you pull up to a stoplight, it gets real noisy because you're getting a direct signal and a reflected signal, and they're combining destructively. I'm canceling out the signal. What did I do to fix it? I moved forward a half wavelength. And what I actually did was move from an area where the phase difference between those two causes them to cancel to an area where the phase difference probably makes the signal stronger than it would be otherwise, because both of those are adding in phase. So I get a very robust signal. Beamforming basically takes that same process but controls it. There's some truly impressive electronics that go behind it, but essentially what they're doing is steering one of those signals in with delay. They're waiting a little bit to transmit it, and what that lets you do is move where those in-phase points add up. And I set it up. I set my media box on the shelf here. I put my display over there. Most of us don't move those. And I'll let the system find what it needs to do in terms of delay to make that those two, the reflected and the direct waves, add constructively at my receiver, at the data sink. Okay? Pretty neat. It's a good way to increase signal to noise ratio. If I have somebody moving around a room, it's possible to do this in real time. I don't know if any of the manufacturers are doing that right now. I couldn't find that. But it's pretty neat. The result is you're decreasing path loss because you're actually using multiple paths simultaneously. 802.11n does the same thing. 802.11n is capable of doing beamforming, and it uses multiple paths as part of what it does. We'll talk about that more when we get into 802.11n. You okay with this? Basically, you're taking phase difference and making it work to your advantage rather than being a disadvantage. I'm controlling something that's destructive, making it constructive. The last one I talked about, and we're going to go an inch deep into this, is something called ultra-wideband. Now, we talked about spread spectrum as being a modulation scheme that took a signal and spread it over a much wider area. UWB does the same thing, except it doesn't modulate anything. It takes a very wide pulse, typically 20% of your center frequency. So if I'm talking 5 gigahertz, I'm going to make a pulse that spans 1 gigahertz. I'm not modulating it. I'm simply putting a pulse there and then turning it off. I'm creating artificial lightning, if you will, or artificial white noise. I can do that real fast. Notice all these other narrowband signals? Look where that one is. Way down below the noise floor. UWB doesn't add to the noise floor measurably, practically, for narrowband services. And so what happens is I use these extremely wide pulses. Remember, I'm in a very contained environment. I know what propagation is going to look like. So I can actually switch this on and off really, really, really fast and move data that way. Think of it as sitting in here with the light switch and being able to pulse that light on and off fast enough. We've actually gone backwards in what we're doing. We're not doing complex modulation. We're just simply doing on and off keying really, really, really fast. At these frequencies, I can make that support tens of gigahertz. What happens when I go past a wall? 60 gigahertz doesn't penetrate very well, so it stops. So I can have these things in adjacent rooms and they won't interfere with each other. I can actually have them in the same room if I want to do a little bit of work behind before I actually create the pulse. If I want to do a little bit of work behind to coordinate them, I can actually have multiple units doing the same thing. And we're not going to go any further into it than that. Just realize this is not a spread spectrum signal. It's just a very wide band, simple on-off signal. Okay? Okay. That's it. I will look at the problems. Thank you for hanging with me through all the computer issues. And we'll see you guys Monday. Be safe. Yes?
Go back.
Go back to which one?
I just got a couple questions.
Ultra-wideband?
The Y-gig.
Oh, Y-gig? Okay. See you, man. Okay. Thanks. Take care.
They got an operating system?
It's not an operating system. It is a device, which, of course, will have an operating system. I don't know if they used a standard one or if they wrote one. Most devices that I've seen in all this stuff use some form of Linux or Unix whittled down so that it only has what they need.
Is this the technology that's going into the wireless HD satellite cable boxes?
Don't know. It wouldn't surprise me.
Because I think they're coming out with wireless boxes so you don't have to run wires.
Yeah. Wouldn't surprise me. This is tightly tied to manufacturer. Who's the manufacturer? Don't know? Okay. You can probably chase backwards, find the manufacturer, and then go to the YGig page and look at who their sponsors are, and it'll tell you.
IEEE's got some little compact computers, basically, little like modems.
Yeah.
Internet modems.
Yeah.
I think they're 32 gigs.
Mm.
Drive set, and they got Ubuntu on it. They got 2 gigs of RAM.
Cool.
And it's got its own little processor on there that you can use for, I guess, the media server.
Yeah. I'm not a hardware designer type, so I purposely haven't dug into how they do it. But you know, an access point is a Linux computer, and I'll bet you that's what that is. See, man. Yeah, this is what I actually pulled off here was a wireless dock where you would take your computer and plug into it, and then all of those other connections are available to your computer. It's just I don't have to stick my computer in there. So.
You're talking about the gaming. There is a company called Steam,
and
they're coming out with their own gaming box.
Cool.
And I think it's probably going to be a lot like this. You can hook up to your TV and to stream all the games from your computer.
Wow.
So I
Really
don't,
neat.
it's, I didn't know how they were going to get where the latency issues would be. It's
You deal with latency in this kind of environment. The latency comes from how long does it take me to process data and then send it across this link. So I've got to put enough processor in, and then I just run the link really, really, really fast. And that's what they're doing, is throwing big bandwidth at it to make the latency go down.
I didn't know how much the theme box was going to be.
It's going to be fun to watch. Here's what I think is going to happen. You know, I've kind of had not quite a hobby, not quite a research interest. It's somewhere in between. But seeing how far I can push 802.11 links in our area. 802.11 is designed to go 300 or 400 feet. I've got links running 30 miles. The record is 240-something miles.
Really?
Yeah, across an ocean, so across part of the Mediterranean from 2 mountaintops. So that's, I don't think, quite fair, but but I pushed them 30 miles across West Kentucky. So what happens when somebody starts doing that with this, changing out antennas, using something else? The other one is optical. Optical, really, really wideband optical is starting to come back. I saw one that has essentially a telescope, you know, big Fresnel optical lens in the front. It has 8 lasers down the side, and it's a transceiver. You know, the lasers transmit. Each of the lasers is running at a different color. You point it at the other end. The lens receives all of them and splits them back out to their receivers. You've got 8 laser links running simultaneously. Pretty cool.